Now, truth values for compound statement with word or. Say, for example, here I am putting a statement that 125 is multiple of 5 or 8. Say this compound statement includes two component statements. Here I am putting component statements. Suppose first component statement is, it includes 125 is multiple of 5. Second component statement is 125 is multiple of 8. Now you can see that this is true. This statement is true. Second statement is false. First statement is true, second statement is false. But if we read this compound statement that 125 is multiple of 5 or 8, because of this word or, because or word is used and this first part is true, even though second part is false, this statement is true. So here P is false, P is true, Q is false, but given statement, given compound statement is true because of word or. If I put here one more example, if we say that suppose 2 into 3, or let me put x plus y whole square equal to x square plus y square, or x plus y whole square equal to x plus y plus 2. Here I have taken this compound statement connecting these two component statements. Here component statements are let me denote them by P and Q. P is x plus y whole square equal to x square plus y square. This is false. This statement is false. Second statement, let me denote it by Q. X plus y whole square equal to x plus y plus 2. This is also false. Both component statements are false. And these are connected by OR. So this total compound statement is false. So here it is clear from this reading of this compound statement, x plus y whole square is equal to x plus y square, or x plus y whole square equal to x plus y plus 2, totally false. So here given compound statement is false. So to be true, at least one part, at least one of component statements must be true. Because here connection is by OR. So to be true, at least one part should be true. Suppose take one more example. Third, 26 is an even number or 26 is divisible by 30, or let me put divisible by, okay, let me give as this 30. 26 is an even number or 26 is divisible by 30. So here P is 26 is an even number. Q is 26 is divisible by 30. P is true. Q is also true. Both P and Q component statements are true, and because these component statements are connected by word OR, the total compound, given compound statement is also true. Therefore, given compound statement is true. So we can put this in a tabular form. Truth table, we say this truth table. P, Q and statement P or Q. So here P or Q, and see notation for P or Q. This type of compound statements P or Q, P or Q, it is also denoted as, this is denoted as P or Q. This symbol is read as OR, P or Q. So this is truth table for P or Q. This is the, see, this symbol is the symbol for substitute of word OR. And previously we discussed that when AND is used, this is denoted as P and Q. This symbol is for AND, this symbol is for OR. So here, this is P, this is Q. So this was P or Q, like that. So this can be denoted by P or Q. So that is the meaning of symbol. This is P, this is Q. This statement can be denoted as P or Q, compound statement. So now truth table as discussed here. If P is true, Q is true, P is true, Q is true, then P or Q, given statement P or Q is also true. If P is true, Q is false, any one is true, other is false, or P is false, Q is true, then also compound statement with OR is true. But if both are false, P is false, Q is false, then compound statement with word OR is false. So this is the way to determine truthness or truth value of compound statement with word or. Now next topic is quantifier. Say these words there exist and for all. These two words are used in mathematics or in a language of laws. Lawyers also use these two language many times because its connection is with logic. These words there exist and for all are said to be quantifier. Say look this statement. Here I have written these three statements. First part is identify quantifier. Identify quantifier. In these statements we identify quantifier. See, first statement is there exists a number which is equal to its square. There exists a number which is equal to its square. So it is about existence of a particular number. And here this word, this is quantifier. There exists. This statement includes there exists. So this is quantifier. Look second statement. For every real number x, x is less than x plus 1. For every real number x, x is less than x plus 1. This is a property. And meaning of this statement is that this property is true for every real number x. So here this word every, for every or for all, meaning is same. This is quantifier. Property is for all members. Here this was for some particular member, particular number. Now look this third statement. There exists a capital for every state in India. You can see that in this statement there are two words, there exist and for every. Now there may be confusion that which one is quantifier, there exist or for every. So observe this statement properly. If you read this properly, then see again I am reading this statement, there exists a capital for every state in India. So here a common property is given for every state in India. This means that every state in India has a capital. Every state of India has a capital. That is the meaning of this statement. So this there exists is a substitute for has. Every state has capital. So in this statement, this is quantifier. This is not quantifier. This is substitute for to have or has. Now, how to write a negation? This is the rule for negation. Any statement having there exist this quantifier, there exist P, its negation is equal to, it will begin from for all. Negation of there exist is for all. then do negation of, make denial of P inside. So say here denial of P, this is P, put here denial of P. As for example, say look here, we want a negation of this statement. There exists a number which is equal to its square. So this is like P. There exists a number which is equal to its square. So consider this as P. There exists a number having this property. Now what we do, it's a negation. Negation is for all, or put every, for every number, this was for there exists a number, it was property for a particular number. Now we are saying that for every number. Now for every number, put denial of P, that means put denial of this statement, which is not equal to its square. For every number, it is not equal to its square. For every number, it is not equal to its square. Second statement, this is beginning from for every. Now how to put negation of statement which is beginning from for every? For every, then this is property. Its negation is negation of every, it begins from there exist, and put negation of inner statement P. For every real number x, x is less than x plus 1. So consider this as P. This is P. For every real number x having property P. Every real number x having property P. Now I am putting its negation. So negation is there exist. Here negation is there exists. There exists real number x. So negation of for every is there exist. Now do write negation of inner property. This is P, so put not P. This is P, so put not P. So such that x is not less than x plus 1. Such that word suits with there exist. There exists real number x such that x is not less than x plus 1. Now here quantifier is for every. When statement is beginning from for every, putting its negation, we begin from there exist. So there exists. Now I am putting here negation. There exists. There exists a state in India which does not have a capital. Which does not have. This was P. There exists capital. It is like P. This is a property. It was P. Now I am putting not P after there exists word. So after there exists word, now I am putting here not P. So not P is which does not have a capital. Which does not have a capital. So few changes of words we make according to English grammar. So this is the method to put negation of quantifiers. Now next topic is implications. If P then Q, such statements are said to be implications. Any statement of this form, if P then Q. Say here, this is conditional statement. Here P is condition. If P then Q, Q is conclusion. So such statements of the form if P then Q are said to be implications. Say look here example. If P then Q, this is example of implication. This is condition. This is conclusion. If P then Q, we can put here component statements. So here component statements are let me say P is a natural number is odd. Then Q means or natural numbers, it's a square, means natural numbers square. Is odd. A natural numbers square is odd. We can't use here it's a natural number square is odd. So these are component statements. If P then Q, so it is implication. Now same statement can be conveyed in 5 different ways. Different ways conveying the same meaning. Same statement can be spoken by different 5 ways. Its meaning remains unchanged. See, the first way is P implies Q. This can be also spoken as P implies Q. So say here I am rewriting this statement, this given statement I am rewriting in 5 different ways conveying same meaning. 5 different ways conveying same meaning are as follows. Say here 1, 2, 3, 4, 5. Application of these 5 methods. See, the first way to speak this statement in different way is P implies Q. P implies Q. We do not repeat the word if then. Instead of if then, what we use? Implies. If P if P then Q, now I am writing by this way, P implies Q. So what is P? A natural number is odd. This is P. Implies Q. So Q is, its square is odd. Its square is odd. So look here, what is written? P implies Q. So this implies is used. If then words are removed. Its notation is P implies Q. We can also replace this word here. This can also be replaced by implies. This is the notation for this word, implies. Now second, see application of this method. P is sufficient condition for Q. For Q, P is sufficient condition for Q. So I am beginning the statement from this part of this statement. For Q, that means for Q. So for a natural number, for a natural number's square to be odd, for a natural number square to be odd, for Q, P is sufficient condition. This is sufficient condition. It is sufficient that what is sufficient? This is sufficient. It is sufficient that it is odd. Means that number is odd. For a natural number square to be odd, it is sufficient that it is odd. Means a natural number is odd. So that is application of second statement. P is sufficient. So this is sufficient. Now third method. P only if Q. P and Q I am joining by only if. So let me put P, a natural number. A natural number is odd. This is P. Now put only if. Only if. Now I am putting Q. Q is, its square is odd. Its square is odd. Then fourth method. Now here Q is necessary condition for P. For P. For P means for a natural number to be odd. For a natural number to be odd. For P. Now Q is necessary. It is necessary that Q. It is necessary that its square is odd. Its square is odd. So this is the way to use necessary and sufficient words. Here we used word sufficient, necessary. Here we used word sufficient. So remember the difference. And sometimes we change location of words according to grammar in English. To put in better way, we change location. As for example, in this method, we begin from 4P. Here we begin from 4Q. Now fifth method. Not Q implies not P. Means negation of Q implies negation of P. Using word implies. So not Q means negation of Q. A natural number's square is not odd. or natural numbers square is not odd. So this is what? Not Q. Then put implies not P. Not P means its square is not odd. Its square is not odd. So this is fifth method. This can also be written as, last fifth statement can also be written as, instead of implies we can join this by if then. If, see, implies is replaced by if then. Implies, P implies Q means if P then Q. So if a natural number square is not odd, then its square is not odd. So these are 5 different ways to express implication. Now converse of if P then Q. Converse of if P then Q is if Q then P. Means converse of P implies Q is Q implies P. And contrapositive of if P then Q is if not Q then not P. This is equivalent statement. Writing a statement by this method, meaning remains unchanged. In converse, meaning is changed, but in contrapositive, meaning remains unchanged. Just we discussed last topic. It was fifth way, different way to express if P then Q. We discussed 5 different ways. This was the last way in discussed example. If not Q then not P, it is contrapositive of if P then Q. Means contrapositive of P implies Q is not Q implies not P. So here meaning remains same. Here meaning is change. Now to understand this converse and contrapositive, we take a question. Write converse and contrapositive of the following statements. If x is a prime, then x is odd. First of all, we put here converse. If x is prime, then x is odd. If P then Q. If P then Q, its converse is if Q then P. So converse is if Q then P. If x is odd, then x is a prime. Meaning is change. Now contrapositive. Contrapositive of if P then Q is if not Q then not P. If P then Q. Now in contrapositive, if not Q, that means x is not odd. This is negation of this statement. then put a negation of P. X is not a prime. P then Q, its contrapositive is if not Q then not P. Here meaning remains the same. Contrapositive means statement with same meaning. Now second example, if two lines are parallel then they do not intersect in the same plane. If P then Q. So first of all converse of if P then Q is if Q then P. So I am putting P. If two lines, if the two lines, they means two lines do not intersect in the same plane, then P, then they are parallel. They are parallel. Now contrapositive. Contrapositive of if P then Q is if not Q then not P. So if negation of this statement, the two lines, see what will be negation of this part? Here word is they do not intersect and its negation will be they intersect. So if the two lines intersect in the same plane, then now negation of this part. Here they are parallel, its negation is they are not parallel, then they are not parallel. So that is contrapositive. Now here converse. Something is cold implies that it has low temperature. Say this part is P, this part is P. Something is cold implies that it has low temperature. This is Q. P implies Q. Now converse is Q implies P. Means if Q then P. So if it has low temperature means something is at a low temperature. If something is at a low temperature, then it is cold. So this is converse. Now contrapositive. P implies Q. Contrapositive is not Q implies not P. That means if not Q then not P. So I am putting negation of this part. If not Q, that means something is not at low temperature. Something is not at low temperature. Then not Q. It is not cold. It is not cold. So say given statement and its a contrapositive, meaning remains same. Something is cold implies it has low temperature. If something is not at low temperature, then it is not cold, meaning is same. Fourth statement, a quadrilateral is a parallelogram if, say here only if word is not given. Here only if not given. If given, not only word is printed. If is given. So that means this is condition. Quadrilateral, parallelogram, diagonals bisect. Parallelogram, diagonals of quadrilateral bisect each other. So this part is P. This part is P, this part is Q. So here I am putting in detail. This can be written as if quadrilateral has, if a quadrilaterals diagonals, if diagonals of a quadrilateral bisect each other, if diagonals of a quadrilateral bisect each other, then it is a parallelogram. Then it is a parallelogram. This is simple form of given statement. So here this part is P. This is P. And this part is Q. So this is simple form. This is simple form of given statement. Now we put converse. Converse of this statement is if P, if Q, then P. Here this is P, this is Q. Now converse is if Q, then P. If a quadrilateral is a parallelogram, if a quadrilateral is a parallelogram, then it is, then its diagonals bisect each other. Then its diagonals bisect each other. Diagonals bisect each other. So this is converse. Now contrapositive. Contrapositive is not Q implies not P. So if a quadrilateral is not a parallelogram,
A quadrilateral is not a parallelogram. Then not P. Its diagonals do not intersect. Its diagonals do not bisect. Each other. So we have written here not Q implies not P. Now here x is an even number implies that x is divisible by 4. So here this is simple. This is P, this is Q. So converse is if x is divisible by 4, then x is an even number. X is an even number. And contrapositive. Contrapositive of this statement is that not Q implies not P. That means if not Q, then not P. If x is not divisible by 4, then it is not an even number. X is not an even number. So that is the way how to write converse and contrapositive. Now, statement of the form if and only if. In mathematics, we observe many statements containing this group of words, if and only if. Now, what is meaning of if and only if when this bunch of words is used? Say, just we discussed implication. If P, then Q. If P, then Q. P is condition, Q is conclusion. If this is true and converse is also true, if Q, then P, this is converse of this statement. So if P then Q and if Q then P, both the way statement is true, then such statements are denoted by this symbol. And between P and Q, either we put this symbol, it means double implies P, double implies Q, or between P and Q we put these words, if and only if. Instead of writing two times P, Q, what we do? We put only one time P and Q and put bunch of these words, if and only if. So meaning of this statement P, if and only if Q is that if P then Q and if Q then P, both the way statement is true. Or this can also be written as Q if and only if P. Sorry, here we should put P. Q if and only if P, or P if and only if Q. Or now see, in this statement, if P then Q, Q is necessary condition for P, and here P is necessary condition for Q. Here P is sufficient condition for Q. Here Q is sufficient condition for P. So P P and Q both are sufficient conditions, both are necessary conditions. So this statement can also be written as P is necessary and sufficient condition for Q and vice versa. That means Q is necessary and sufficient condition for P. So when this both parts are true, that means both P and Q are necessary and sufficient conditions. So these are four ways. Meaning is same. This is the meaning of these statements. Now to understand in this question, say question is rewrite following statement in the form P if and only if Q. This is the question. Now look, if you watch the television, then your mind is free. If you watch television, then your mind is free. This is like if P then Q, and if Q then P. Look, this part is same. You watch television, look this part, your mind is free. So what is it? If this is P, this is Q, then here it is given that if P then Q and if Q then P. If P then Q and if Q then P. Now this can be written as this method. P if and only if Q. So here P is you watch television. This is P. Write P. Then put bunch of words. If and only if. If and only if. Now Q. Q is your mind is free. So this is in the form P if and only if Q. Similarly, second statement. If a quadrilateral is equiangular, then it is a rectangular, and if a quadrilateral is a rectangle, it is a rectangle. Sorry, here I did mistake. Rectangle. If a quadrilateral is rectangle, then it is equiangular. So see, this part is same. Let me call P. This is Q. So if P then Q and if Q then P. P then Q and if Q then P. So this can be written as this can be written as P if and only if Q. So here answer is a quadrilateral is equiangular. This is P. Then bunch of words. If and only if. If and only if. Second part is Q. It is a rectangle. Now write a negation. So here statement is for every positive real number x, the number x minus 1 is also positive. Something is given, a property is given for every positive real number. So quantifier is given and we want negation of any statement beginning by word every P. its negation is, what we do, there exists, its negation will be beginning from there exist, and we keep negation of inner property. This is the way which we discussed. So say, for every positive number x minus 1 is also positive. Now we want its negation. So its negation is, say here, now I am putting a negation of this number. So by this rule, there exists a real number x. This was for all. This is for some particular member. So we put a real number x. Now we deny this property. Put denial of this property. The number, there exists a real number x such that, now denial of this property for this particular number is x minus 1 is not positive. So we put a negation of a property. Here this is property, x minus 1 is positive, here x minus 1 is not positive. Say here, negation. All means every cat's scratch. This is property, that cat's scratch. So its negation is, there exists a cat. There exists a cat which does not scratch, which does not scratch. Here, by similar method, for every real number x, either x more than 1 or x less than 1, this is property for all real numbers x. Now its negation is, there exists a real number x such that, see, whenever we begin statement with there exists, then with there exists these words suit. Such that, now negation of this property, neither x more than 1 nor x less than 1. So negation of either or is neither nor. Now here, there exists a number x such that 0 less than x less than 1. So its negation is, when statement is beginning from there exists, we can put negation by this way. We can also use by simple way, that there does not exist. There does not exist a number x such that 0 less than x less than 1. Or we can also put its negation by this property, that negation of there exists p, it is equal to, for every, begin from for every, then put negation of inner property. Negation of there exists is for every, then put a negation of inner part. So using this property, this negation of this can be also written as, for every number x For every number x, now negation of this is that this is x lies between open interval 0 to 1, and here its negation is x does not belong to 0 to 1. So for every every number x, x does not belong to 0 to 1. So this is also a way to put a negation of statements beginning from there exists.